Hello, I'm Kidon Lee from Portland State University. Today, my presentation topic is weld penetration model based on coaxial image and photodiode signal during laser welding of aluminum and copper overlap joints. Many countries are planning to ban internal combustion engines. Accordingly, automotive industry are developing eco-friendly vehicles as like electric and hybrid cars. As the increasing of demand for eco-friendly vehicles, the growth of secondary battery market is expected to be explode. To increase the productivity, high-speed joining process is required. So, laser welding process is already adopted in battery manufacturing for the assembly. However, laser welding is fusion welding. It means that formation of intermetallic compounds are unavoidable. When we perform the laser welding on aluminum copper joint, which is used in battery tap, IMCs can be easily formed. As shown in the left graph, excessive intermetallic compounds into the weld deteriorate the strength and electrical conductivity of the weld zone. As the penetration depth increases, the dilution between aluminum and copper increased. As a result, amount of IMC was occurred into the weld and the mechanical strength was decreased. Therefore, we saw that the penetration depth is an important factor related to the quality of the weld. YAG laser used in industries has low energy absorption rate for aluminum and copper. Thus, keyhole can be collapsed frequently, resulting in unstable penetration depth and defect. The need for quality monitoring is maximized in partial penetration weld because the backside was not visible. Thus, real-time quality inspection is necessary at the top bit in order to monitor the penetration depth and detect in partial penetration welding case. Companies need the solution for quality inspection during laser welding. Many of laser markers has been developed keyhole depth monitoring system for real-time quality inspection. As you know, that keyhole depth monitoring system is relatively expensive than other sensors. So, it is difficult to apply it to the field easily. Therefore, it is necessary to develop alternative methods for real-time monitoring, measuring the penetration depth during aluminum copper overlapped laser welding. Recently, a lot of CNN model has been developed used in image data. In previous study for aluminum copper laser welding, we figured out that the correlation between the weld pool image and penetration depth. As like here, significant change were observed when the penetration depth was varied as like A to B. It indicated that penetration depth can be estimated from the weld pool size observations, real time or not. In addition, we tested photodiode sensor as the alternate as shown in spectral intensity. Measured the intensity was changed depending on the penetration depth. With the increasing of laser power, deeper penetration was achieved, and the kappa element peak intensity became stronger with a wavelength of 578 nanometers. It means that the penetration and weld quality can be predicted by detect the specific spectra relate with the vaporized element at low plate because penetration depth and photodiode data were associated. In this study, we aimed to predict the penetration depth through image data and photodiode data using CNN models. Also, we compared the two predictive CNN models use image data only and multisensor fusion data, combining of image data and photodiode data. This slide shows the experimental setup. Used material are aluminum 1050 and C1100, and overlapped welding was performed as like here in the upper right picture. Laser welding performed by disc laser and the high-speed camera was installed to obtain coaxial image data. The photodiode data was gained non-coaxially. The penetration depth data were obtained using a keyword depth monitoring system made by Trump. Totally, three different kinds of sensors were applied at different measurement frequencies. The, the image data were gained at 10,000 fps. The photodiode was 20 kHz and the keyword depth was 7 kHz. Welding conditions are as follow. Laser power and welding speed was varied as like here, and focal length was fixed. During the welding, the shielding gases were not provided. We tested 25 classes experimental conditions. This figure shows the synchronized high-speed camera movies and keyword depth data. As already mentioned, the input data and output data used in CNN were measured at different rates, so data pre-processing was required. The image data was mono with this resolution. Data pre-processing was progressed by combining 100 air image data and the average intensity value for each pixel was calculated. Finally, it was downsampled up to 0.1 kHz. Pre-processing image data was provided at the lower left picture. As you can see, the noise was reduced and where the characteristics was more emphasized. This slide shows the sequence of pre-processing of photodiode data. At first, the photodiode signal was downsampled to 10 kHz by averaging about 5 datas. The data was downsampled to 0.1 kHz using transfer function to maintain the characteristics. of time-dependent data. This slide shows the pre-processing of penetration depth monitoring data. The output data, penetration depth data, was collected with rate of 7 kHz. Penetration depth data averaged every 70 data to perform a downsample to 0.1 kHz. After data pre-processing, the learning was conducted in two structures. One is image CNN using image data only as the input data, and second is multisensor fusion CNN using image data and photodiode data. The basic structure both of CNNs were consisted of the same structure. Lelu was used for the activation function, and the batch normalization layer was placed between the convolution layer and the pooling layer. Total of 2115 datasets were obtained, randomly selected for data collection and data preprocessing, which were divided three kind of group: 1418 training dataset, 370 validation dataset, and 318 testing datasets. Adam was adapted as optimization functions, and mean square errors was used as loss function. Mini-batch gradient descent method was applied to learning. Batch size was 16, and the number of learning was 1000. This slide shows the overfitting of CNN model applied in this study. As shown that overfitting of CNN model synthesis was expressed via a loss approach graph. Both of image CNN and multifusion CNN show a sharp decrease in loss early in learning. After epoch 300 and above, loss for validation dataset converges without divergence. We confirmed that either CNN learning model not occur overfitting. This presents the predicted result of the training dataset. The graph above is the result of image CNN models, and below is the result of multisensor fusion CNN models. Both models shows high decision coefficient, result 0.99, and low MAPE. In particular, the multisensor fusion CNN shows 0.11% MAPE, which is lower than that of image CNN model. The calculation method for MAPE was given at below the graph. The following are the prediction results for the test dataset. The left graph is for the image CNN, and the right graph is for the multi-sensor fusion CNN. Both CNN tests have a determination coefficient of 0.98, and the multi-sensor fusion CNN has a MAPE of 1.86%, which is 0.19% lower than the image CNN. Finally, we compare the residuals of prediction results for the test dataset through the box plot. Through the penetration result on the test dataset, it was recognized that the penetration depth could be accurately predict using the multiple image data. Furthermore, we found that the means of residuals was close to zero. It indicated that both of models was not biased. CNN learning use image CNN has high accuracy. However, addition of photodiode data supplied further high accuracy. Using the multisensor fusion CNN model, we found that the gap between 1% and 99% and min and max has narrowed. As a result, data prediction was more reliable when adding photodiode data. We also found the leveraging the multisensor fusion CNN model reduced the variance in residuals and allow more reliable learning. This is conclusion. Thank you for your attention.